Greetings, and we will resume our discussion on the Lagrangian formulation of equations of motion, and I will quickly recapitulate the essential consideration that we had undertaken, that a mechanical system is considered to evolve in such a way that action would be an extremum. That is the principle of extremum action, as it is called. This is also referred to as the Hamilton's principle, and this is a big departure from the Newtonian formulation, because in Newtonian formulation we agreed that a mechanical system evolves in such a way that it responds to the stimulus which is imparted to the system by a force. So there is a cause effect relationship, which is the principle of causality, which is the important consideration and a fundamental consideration in Newtonian mechanics, and the entire evolution of the mechanical system is described in terms of the Galilean principle of relativity. And secondly, any departure from equilibrium is explained in terms of the cause effect relationship which is contained in Newton's second law, the principle of causality. So that is the governing principle of Newtonian mechanics. The governing principle over here has nothing to do with causality, it has nothing to do with force, it deals with the principle of variation. It stipulates that you set up what is called as a Lagrangian for the system, and we have not mentioned as yet how to set up the Lagrangian, we have not gotten there. We only know that it is some function of position and velocity, and in general it is a function of q, q dot and t, okay. But what kind of a function it is we have not described as yet, and never mind, we will work with it, and at some point we will have to answer this question, that what is the recipe to set up the Lagrangian. So we will take it up at that point. In the meantime, we carry forward the same starting point as in Newtonian mechanics, that a mechanical system is described by a point in phase space by position and velocity, but rather than by position and velocity directly, it is represented by a function of position and velocity, which is the Lagrangian. So the Lagrangian is a function of q and q dot, and this function, if you define an integral which is known as the action is the integral L dt from t1 to t2, that this action must be an extremum. So this is the principle, this is the governing principle on which the evolution of a mechanical system is described. Now what this led us to, and these are some of the major steps that we discussed in the last class, so I will not go through this in any detail now, but quickly recapitulate that if this is an extremum, then any variation in this would of course vanish, and a variation with respect to what? A variation with respect to different paths in the phase space, in the position velocity phase space that a system can take. So these are like different world lines, different paths that the system can take, and variations with respect to these paths will lead to an action integral which will remain stationary, it will not change if you go from one path to a neighboring path which is somewhat close to the previous one, to some reference path which we know would be the one that the system will evolve along, okay. So this differential increment in action would vanish, which we have restated in the equation we have at the middle of the screen here. Now these are the alternative paths that one can think of. So this is the position velocity phase space. We consider the evolution of a system from time t1 where the point with coordinates q and q dot describe the state of the system, and at a later time t2 the system gets to this point along a certain path, and this is some wiggly arbitrary path, it could even cross itself, whatever it is, right, it is some path that the system would take, and at a later time t2 it gets to this point. Now I show an alternative path over here in this different color, which is a slightly different color, it is beige I think, I am not good at identifying colors. So this is I suspect beige, and you can think of a slightly different path, and at some intermediate time between t1 and t2 the system would be at different points, at some specific points on each of these two paths. So let us say that if it were to evolve along the white path, if the system is at this point at a certain time t, then at the same instant of time if the system were to evolve along the beige colored path, the system would be here, and the horizontal distance between these two is the delta q at the time t, and this delta q at the time t, as you can see from this figure, is obviously 0 at the start and at the end, it cannot be anything else. If it is non-zero, it can only be in between t1 and t2, but not at the start and not at the finish, those points are fixed, there is no variation delta q there. So here you have the term in which delta q vanishes, and the remaining terms can be combined together, and this is how far we had come. So this term vanished and the remaining terms have been put together in this expression here, and now you are left with this term, which is the first term amongst these three, and the last term, and these two terms are put together. This is an integral del L over del q delta q dt. So this del L over del q delta q dt, this is coming from the first term, and from the second term you have this expression here. Is that clear? Now in this, delta q is appearing in our analysis because we are choosing different paths, and there is no reason to suspect that the beige colored path that we had in our previous figure is the only alternative to the white colored path that we considered. We could think of n number of alternatives, hajar paths, right, any different variation, anything which is other than the path that the system would actually take. So any of those paths could be taken, and therefore this delta q is a completely arbitrary increment in q. There is nothing special about that particular delta q or delta q dot that we had in the previous figure, that was just one of the infinitely many variations that one can think of. So this variation being arbitrary, now you are confronted with a very simple situation that you have a definite integral from t1 to t2, it is an integral over time, so that is indicated by this dt at the end, and the integrand, what is being integrated out is a product of two factors, one is a factor in this beautiful bracket and the other factor is delta q, right. The integrand is expressed as a product of two factors, of which one is completely arbitrary, and no matter what this arbitrary delta q is, the total integral must go to 0, and for arbitrary delta q this can happen if and only if the factor which is inside this beautiful bracket is identically 0. Okay? So that comes as a necessary condition that the principle of variation holds, and this is the condition, the factor which is inside this beautiful bracket must go to 0 and this is what we call as the Lagrange equation. How has it emerged? It comes as a necessary condition that action is an extremum. So, we begin with the requirement, we demand that action must be an extremum, and then ask if action is to be an extremum, what is the condition that must be satisfied. This condition is that a certain equation must hold, the term which is inside this beautiful bracket must vanish. So, the equality of this term inside the beautiful bracket is the necessary equation which must be satisfied, and this equation is what is called as the Lagrange's equation. Now, we have the Lagrange's equation, but we do not have the Lagrangian itself. We have not discussed even as yet what is the recipe to construct the Lagrangian. The only thing we know about it is that it is a function of q and q dot. So, we will have to of course address this, because otherwise if we do not know what the Lagrangian is, we cannot get its partial derivative with respect to q and we cannot proceed, nor can we get its partial derivative with respect to q dot, because we have to know what is the mathematical dependence on q of L and how does L depend on q dot. So, unless we know this, we cannot really do anything with this equation. So, let us see how we can get it. This is the Lagrange's equation. What we do know is that space is homogeneous and isotropic. The space we are dealing with is isotropic, its properties are the same in all directions, and therefore the Lagrangian cannot depend on any specific direction, because properties of the space are the same. That is what is meant by isotropic, right. Properties of the space being isotropic, the Lagrangian cannot depend on the velocity. So, we are looking for a Lagrangian which depends on velocity, but not on the direction of velocity. So, what is the quantity that you can construct from the velocity which does not depend on the direction of the velocity? It can be v dot v, v being the velocity, the dot product of v with itself is v dot v, and this does not depend on the direction of v, it is a scalar, right.
Rather you can say it is the speed.
It is the speed. So, you can construct a quantity if it depends on velocity. The only function of velocity which is independent of direction is the quadratic function of velocity. Okay? The speed comes from the square root of v dot v. Okay? So, it must depend quadratically on the velocity, and therefore, we pick a function f1 which is a quadratic function of q dot. Q dot is our velocity. So, we expect the Lagrangian to be a quadratic function of velocity, and we take the simplest functions. Okay. As they say, do not trouble trouble unless trouble troubles you. So, why do you look for more complicated functions? Look for the simplest function. What is the simplest function that you can think of? Position, some function of q, call it f2q. Simplest function of velocity which does not depend on velocity, it will be a function of q dot square. That makes the Lagrangian a sum of f1 and f2, f1 being a function of q dot square and f2 being a function of q. Now, we have made some progress. We have still not identified what is the function f2 of q. Is f2 equal to alpha q? Is it alpha q plus beta q square? Any polynomial function of q would meet the requirement that it is a function of q, right. So, we have still not pinned down the exact functions, and that is what we will do now. We take the simplest function of q which depends on the position, and we know that the potential energy depends on position, right. So that is a mechanical property that we are familiar with, which we expect to be of great value in any mechanical discussion, any discussion on mechanics. So we take the potential, we propose that the function f2q be chosen so that it is the negative potential energy. We make this proposal, we will still have to justify this proposal. Okay, we have made this proposal with a certain hope that it will turn out to be a good proposal. We have not provided reasons for it, because we could think of other functions as well. So we propose at this point that the function f2q be chosen so that it is negative of the potential energy function minus v of q, and the simplest function of quadratic function of velocity is of course the kinetic energy, the half mv square. So we propose that m2 q dot square, in which we have identified the inertia. What we have done is we are choosing f1 to be the simplest function of q dot square, and the simplest function of q dot square is just some constant times q dot square, right. That constant we choose to be half the inertia, half the mass. Why do we make that choice? We still have to rationalize it, we will. Okay. So we make this proposal that f2q be chosen so that it is minus v of q. We propose that f1 q dot square be proposed as m by 2 times q dot square. This will identify the Lagrangian as t minus v, and we hope to justify this choice. Okay. Now what justifies this choice is a question we must now answer. Now just ask yourself, what will this combination, because m by 2 q dot square will be the kinetic energy, and this is now giving us the difference between the kinetic energy and the potential energy for the Lagrangian function. And now you can take the partial derivatives, because you have written L as a function of q. So the partial derivative of L with respect to q will be simply minus del v by del q, and you can also take the partial derivative of the Lagrangian with respect to q dot, because that will simply be m by 2 times twice q dot. So you can determine these derivatives, and you can put these partial derivatives in the Lagrange's equation and ask yourself, or what do you get? The partial derivative of the Lagrangian with respect to q, which is the negative of the partial derivative of the potential energy function with q. The negative gradient of the potential in Newtonian mechanics is the force. So we get the force from this term, and from the other term we get the momentum. And then in the Lagrange equation you have got the time derivative of the momentum. So you will get dp by dt, which is the Newtonian force, right. So essentially what you get is Newton's second law. Okay. Do you see that? Now this is what justifies our choice of f1 and f2, that f1 and f2, let me go back to the previous slide one more time, that the proposal here was the Lagrangian be expressed as a quadratic function of q dot and another function and a sum of another function of q. So far so good, and then we choose these functions to be respectively the kinetic energy and the potential energy with a minus sign over here, and this particular choice turns out to be extremely profitable, because it gives us results which are completely consistent with Newtonian formulation of mechanics. Now, Lagrangian formulation or Hamilton's formulation is an alternative formulation, but it is not going to give us anything different. If it is in contradiction with Newtonian mechanics, there will be trouble. So, it is important that the results which come out of this are completely consistent with Newtonian mechanics, and this consistency is now explicitly manifest. And what makes this consistency, what makes it possible for us to attain this consistency is the proposal that the Lagrangian is written as m by 2 q dot square. We did not provide any rationalization for the factor m by 2. We said that we will take the simplest function of q dot square, which is just a linear function of q dot square, like alpha times q dot square or k times q dot square, and I suggested that let us choose that proportionality to be half the inertia m by 2. And now we see that that particular choice m by 2 q dot square is what gives this del L by del q dot to be inertia times the velocity, which is the momentum. So, that choice turns out to be a particularly productive one, a particularly useful one, and this is what enables us identify the Lagrangian as t minus v. Now, this I will not say is a very standard recipe to construct the Lagrangian. When you go to more complicated situations, one has to keep track of many other fairly subtle factors. You have to ask, is this Lagrangian invariant with respect to Galilean transformations? If you are doing relativistic mechanics, you will have to ask, is the so called Lagrangian that you will then set up consistent with the Lorentz transformations, etc. So, there are many additional questions that you need to answer, and in this introductory discussion there is no room for such involved issues, but we do have a basic foundation, and this works for a good part of mechanics, that you can define the Lagrangian as t minus v, and this also suggests to us a recipe to do other problems, because hereafter we will not recognize momentum as mass times velocity, which is the Newtonian definition of momentum. We will rather use the Lagrangian definition of momentum, that it is the partial derivative of the Lagrangian with respect to the velocity. So, del L by del q dot is our definition of momentum, and hereafter whenever we talk about momentum, we will talk about del L by del q dot and not mass times velocity. This is what is called as the generalized momentum. Okay, the definition of generalized momentum is that it is a partial derivative of the Lagrangian with respect to the velocity, and we can see a suggestion toward this from this correspondence which we see over here. So, this is our generalized momentum del L by del q dot, and that is the term we shall use in the future. And what we have achieved by this particular recognition of Lagrangian as t minus v is a complete equivalence with Newtonian formulation. The foundations are completely different. The foundation of Newtonian mechanics is the principle of causality, the cause effect relationship, the linear response formalism. The foundation of Lagrangian mechanics is the principle of variation. They have nothing to do with each other, these are completely independent formulations, you cannot derive one from the other. These are independent formulations, but they must converge and they must provide you with essentially the same results as long as you work within the domain of classical mechanics. Things change when you go over to quantum theory, that is a different story. Okay? But in classical mechanics, Newtonian formulations and the Lagrangian or Hamiltonian formulation, they must give you essentially the same results, and here we find that yes, indeed there is such a correspondence. Now, let us write a more general Lagrangian, which is a function of q, q dot and t, which is sometimes the case, and we will very soon see when t must be included and when it need not be included. If you have an isolated system and there are no missing degrees of freedom, and I discussed this in a different context earlier, but I think that example is a very useful one, that if you are moving an object on a surface, you know that there is friction at the surface, and if you set up the equations of motion only for this bottle but do not include the particles of the table which are also interacting with this, then you do not have an isolated system, right. Then this system is interacting with something which is not taken into account in your equations of motion, and then it will show up as missing degrees of freedom. Okay. So, when you do not have any missing degrees of freedom, you will not have the Lagrangian to have any explicit time dependence, but the Lagrangian will always have an implicit time dependence, and the implicit time dependence means that the Lagrangian depends on time by the virtue of its dependence on position and also by the virtue of its dependence on velocity, virtue or vice, however you look at it. Okay. But it is because of that reason, because the Lagrangian depends on q and q depends on time, the Lagrangian becomes a function of time. So, such a dependence is what is called as implicit dependence, and if there are missing degrees of freedom, there may also be an explicit time dependence. So, the general expression for the time derivative of the Lagrangian will come from its implicit dependence on time through its dependence on q, which in turn depends on time. So, there is a dq by dt over here, and a dependence on of the Lagrangian on the velocity, which in turn depends on time. So, there will be a d by dt of q dot, which is q double dot, which is the middle term that you see, and then there will be a possible explicit time dependence which is shown in the third term, in the last term. So, this is the complete expression for the total derivative, total time derivative of a Lagrangian. Now, from the Lagrange's equations, and here it is, this is the Lagrange's equation, these two brackets must be equal to each other, the difference goes to 0. So, del L by del Q is d by dt of del L by del Q dot, right, and this del L by del Q is replaced by d by dt of del L by del Q dot in this step over here. Then you have this term which is del L by del Q dot times the second derivative of Q, which is here, and then you have the explicit time dependence of the Lagrangian coming in the third term. And if you look at these two terms, they are algebraically completely equivalent to the derivative of a product of two functions, because the derivative of a product of two functions is one function multiplied by the derivative of the second plus the second function times the derivative of the first, which is q double dot, right. So, you have only rewritten this algebraically as d by dt of a product of these two functions. The last term shows up over here, and essentially if you take, now this term is a total derivative of the Lagrangian, this is a total derivative of a product of these two functions. So, I move this term to the left, it comes to the other side, or rather I move this del L by del T to the other side and move this to the right. Okay. So, just a rearrangement of these terms gives us this relationship over here, that the total time derivative of the difference between the first term and the Lagrangian, the first term being a product of two functions. There is no power to my laptop. So, we are looking at the total time derivative of the Lagrangian, which comes from implicit dependence on time through the explicit dependence on position and velocity, which are explicit functions of time, and a possible explicit dependence of the Lagrangian on time directly, which may come from the missing degrees of freedom. So, we make use of the Lagrange's equation, because from the Lagrange's equation we know that these two terms are equal, the difference going to 0. We express del L by del Q as the time derivative of this quantity over here, which we already know is the generalized momentum. That is our definition of the generalized momentum. And then we combine the first two terms and write this as a time derivative of a product of two functions. So far so good. Now, if we rearrange the terms in this last equation, we get the time derivative of this difference equal to minus del L by del T. So, you move this del L by del T to the other side and move this dl by dt to this side. Okay? So, you have only minus del L by del T on one side, and this tells us something very interesting. It tells us that in case the Lagrangian does not have any explicit time dependence, then the partial derivative of the Lagrangian with respect to time will vanish, right. So, we recognize the condition under which the left hand side is the total time derivative of a quantity vanishes, because if del L by del T is equal to 0, which is the meaning of the Lagrangian not having any explicit time dependence, right. If the Lagrangian does not have any explicit time dependence, del L by del T will go to 0, and then d by dt of this bracket must vanish, and if the derivative of a certain quantity goes to 0, that quantity must be a constant. So, here we are. So, del L by del T being 0 now guarantees that this particular function is a constant, and this function is called as the Hamilton's principal function. This is the definition of Hamilton's principal function. It is del L by del Q dot times Q dot minus the Lagrangian, okay, and del L by del Q dot is our definition of the generalized momentum. So, the definition of our Hamilton's principal function is that it is PQ dot minus the Lagrangian. This is the definition and the meaning of Hamilton's principal function. We know that it is a constant if and only if the Lagrangian does not have any explicit time dependence. We have also seen the correspondence with Newtonian mechanics through these partial derivatives, which we have shown earlier, and we can ask ourselves, what is it further that we can learn from this correspondence. Now, if you see this PQ dot minus L and look at these quantities, the right hand side, from the Newtonian perspective, by exploiting this correspondence further, you see that PQ dot is mass times velocity, which is mv square, right, and you have got mv square minus the Lagrangian. The Lagrangian is kinetic energy minus the potential energy, and therefore, the Hamilton's principal function is 2t minus the Lagrangian, which is 2t minus the difference of kinetic energy and the potential energy, which essentially gives a meaning to the Hamilton's principal function, because what comes out of this is t plus v, which is obviously the total energy of the system, right. So, the Hamiltonian, which we have defined as the Hamilton's principal function, can be immediately identified with the total energy, which is a conserved quantity, which is a constant quantity, and the constancy is not a matter of faith, it is expressed by the previous result that it has come from this d by dt of this Hamilton's principal function goes to 0 whenever del L by del t is 0, right. So, it is not just a matter of faith, it has come as a result of this particular condition. What is the condition? That the Lagrangian must be, whatever time dependence it has, must be only through q and through q dot and not direct. So, there should be no explicit time dependence that the Lagrangian can have, and if and only if the Lagrangian does not have any explicit time dependence, will the Hamilton's principal function correspond to the total energy, which is a conserved quantity. And do you see the Noether's theorem talking to you in this result? Because the Lagrangian being independent of time is a symmetry, that the Lagrangian will remain the same whether you formulate it yesterday, today or tomorrow or even day after tomorrow, right. That is a symmetry. It is a symmetry with respect to translation along the time axis. Any time in the past, present or future, the Lagrangian remains the same, because no information is missing, no degrees of freedom are lost. Okay. You can't do that if you were to include friction, because every time you do this, okay, there will be differences in the interaction, they have not been taken explicitly into account explicitly in your analysis, so they are left out, right. So, when the Lagrangian is independent of time, you have a symmetry with respect to changes in time. Time is a parameter with respect to which the Lagrangian is invariant, and this invariance is a symmetry principle, and associated with this symmetry is a conserved quantity, which is the energy. The energy is a constant, and you can see a manifestation of the Noether's theorem, that associated with every symmetry principle there is a conservation law and vice versa. Okay. Now, this has come so neatly from the Lagrangian formulation. You can generalize this. If there are n degrees of freedom, you can put a subscript on p and q dot and write the Hamilton's principal function as a summation over I going from 1 through n. So, this is a straightforward extension, and let me remind you that the object of this course is not to get into the details of Lagrangian formulation or into the details of Hamiltonian formulation. This is an introductory course in classical mechanics. Okay. It is what students would take as one of the first courses in classical mechanics after high school or at some undergraduate level, and at that level one would not take up any involved problems in classical mechanics in the Lagrangian formulation or Hamiltonian formulation. So, we will not take up systems with many degrees of freedom and so on, we will only illustrate some examples. The focus of this course is to reveal an alternative formulation of classical mechanics, that in as much as Newtonian mechanics is inspired by the principle of inertia, Galileo's interpretation of equilibrium, which goes into the first law, and Newton's interpretation of departures from the first law from equilibrium generated by interactions revealed by the cause effect relationships contained in the equation F equal to ma, which is the second law, that an alternative formulation of mechanics exists and it has a charm of its own. it has a beauty of its own. It is based on a completely different principle, and it is this alternative that we are introducing the students to in this course. The quantities we are going to be dealing with in this formulation will be the generalized coordinate, the generalized velocity, and the generalized momentum. So, we shall no longer talk about coordinate as if it is just a position coordinate in a Cartesian geometry. Okay. And the definition of the generalized momentum requires the Lagrangian to be set up, because unless you set up the Lagrangian, you cannot determine its partial derivative with respect to q dot. So, you set up the Lagrangian, take its partial derivative with respect to q dot, then you know what the generalized momentum is. Till then it is not known to us. We have seen that it reveals a connection between symmetry and conservation law. We have already seen one such illustration, but because of the fact that this formulation is so general, this can be very easily extended to other expressions of the Noether's theorem, and I will illustrate one other. This is the one that we have already seen, that the Lagrangian of a closed system does not depend explicitly on time, therefore del L by del T is 0. This is a symmetry principle. Associated with this is a conservation principle, that the Hamilton's principal function is a constant, and it is this that you call as the total energy. So, there is a connection between symmetry and conservation law that we have seen over here. It is in this context that you call the Hamilton's principal function as the energy, otherwise you simply call it as Hamilton's principal function. Okay? But when it is a constant, you call it as the energy. Now, let us consider another symmetry. We will now consider symmetry with respect to space. We considered symmetry with respect to time, del L by del T being 0 is symmetry with respect to time, the same Lagrangian any point of time. So, that its partial derivative vanishes, right. Now, we consider changes in the Lagrangian because of translational displacements of the system. Is there any invariance coming because of this? And this invariance would obviously come in homogeneous space. If the space is homogeneous, you cannot have a different Lagrangian, right. So, delta L changes in the Lagrangian because of changes in the coordinates, and just to illustrate this, I make use of the Cartesian coordinates, which is the simplest or most familiar coordinate system that people use. So, this delta L will be determined by partial derivative of L with respect to x times the displacement delta x plus similar term from the dependence of the Lagrangian, if any, on y, and likewise there is a term involving the z coordinate. And if this delta L is equal to 0, no matter what delta x is, no matter what delta y is, no matter what the delta z is, the sum of these three terms is not going to 0, because delta x, delta y, delta z take some special values which adjust to each other, so that the sum of the three terms can go to 0, right. You can always have 2 plus 1 minus 3 equal to 0, sum of three terms going to 0, right, when none of the three terms is individually 0. This cannot be the case, because delta x, delta y, delta z are arbitrary displacements. So, no matter what delta x is, no matter what delta y is, and no matter what delta z is, if delta L is 0, and this is a statement of symmetry, right, it is coming from the homogeneity of space, and del L by del Q must be 0 no matter what delta x, delta y, delta z is, right. So, this result del L by del Q equal to 0 comes from the consideration of space being homogeneous. And now we make use of the Lagrange's equation, because del L by del Q minus time derivative of this term is equal to 0, and del L by del Q is 0, which means that this time derivative of this factor is 0. This is of course the momentum, which means that the time derivative of the momentum is 0, or if the derivative of a function goes to 0, that function must be a constant. So we have got a conservation principle, exactly, yeah, that is absolutely right. So you see that the conservation of momentum keeps coming every time there is a symmetry. Earlier we met the symmetry with respect to time, now we meet symmetry with respect to translational displacements in homogeneous space. We have discussed this earlier in the context of Newtonian mechanics, but here you see how it comes very naturally and easily out of Lagrange's equations. And you know that whenever the Lagrangian is independent of this coordinate q, is what would happen if del L by del Q goes to 0. Every time the Lagrangian is independent of a degree of freedom q, the corresponding momentum will be constant. Now this is a connection again between symmetry and conservation law. So del L by del Q equal to 0 guarantees that del L by del Q dot equal to P is conserved, and the law of conservation of momentum, it arises from the homogeneity of space. And this is very nicely stated by this very well known law, that the momentum which is canonically conjugate to a cyclic coordinate is conserved. Okay. Whenever the Lagrangian is independent of a coordinate, this coordinate is said to be a cyclic coordinate. Okay, that is the meaning of a cyclic coordinate. A cyclic coordinate is one which does not appear in the Lagrangian. Okay, and if the Lagrangian is independent of that coordinate, its partial derivative with respect to q vanishes, and therefore the partial derivative of the Lagrangian with respect to q dot, the corresponding velocity, which is what gives you the corresponding momentum, and this is this correspondence is what is implied by the term of canonical conjugation. This canonical conjugation refers to this particular explicit correspondence between momentum and position. Okay. So the momentum p is said to be canonically conjugate to a coordinate if it is given by the partial derivative of the Lagrangian with respect to the corresponding velocity del L by del Q dot. Okay. So that is the momentum, and the momentum which is canonically conjugate to a cyclic coordinate is conserved. Now you can, like I said, extend this to many degrees of freedom. You will have to sum over all the degrees of freedom. So it is essentially the same original expression for the Hamiltonian which you write for all degrees of freedom. And now you ask, you make demands on the properties of the Hamiltonian. What would be a differential increment in the Hamilton's principal function? So this dH will get its increment from changes in qk dots, which are changes in the velocities, changes in the momenta because the product is coming in the Hamiltonian, and because of changes in the Lagrangian, right. So the increment in dH in the Hamilton's principal function comes from change in this product, and this product can change because of either of these two terms. So it will be the first function times increment in the second, and the second function and increment in the first. So they are both contributors. So the change in the product qk dot pk will be a sum of the first two terms, right. and then you must subtract from this, because of this minus sign, the increment or the change in the Lagrangian, which will come because of the dependence of the Lagrangian on q and a change in q, and because of the dependence of the Lagrangian on the velocity and the change in velocity, and of course you must sum over all the degrees of freedom. Okay. So, each term has been summed over k, but there is something we ought to notice, and some of you would have already noticed, that if you look at the first term and the last term, both involve increments in the velocity dq dot, right, and for each degree of freedom, a degree of freedom is necessarily independent, right. The corresponding coefficients must be equal, because this one comes with a plus sign and this one comes with a minus sign. So, these two terms must cancel each other, right, they must cancel each other, because del L by del Q dot is nothing but the momentum itself. Momentum, what is P? It is the partial derivative of the Lagrangian with respect to the velocity. So, those two terms cancel and you are left with only the middle two terms, and in the middle two terms the coefficient of dq in the second term is del L by del Q, which is equal to the time derivative of the momentum, as we know from Lagrange's equation, because Lagrange's equation tells us that del L by del Q must be equal to d by dt of the corresponding momentum, right. So, del L by del Q has now been identified as P dot, okay. The subscripts k must be kept track of, you must sum over all the terms, and this is now our expression for the increment in the Hamilton's principal function. Now, Hamilton's principal function, the way Hamiltonian mechanics is done, must be written as a function of position and momentum and not as a function of position and velocity. Now, these are two different formulations, the Lagrangian formulation and the Hamiltonian formulation, and I am going to rub this point in, I am going to harp on this a number of times even at the cost of repetition. The Lagrangian formulation must be used in terms of position and velocity, and the Hamilton's formulation must be used in terms of position and momentum. Okay. So, we express the Hamiltonian as a function of position q and momentum p, either position and momentum or momentum and position, it is the same thing, it does not matter which one you write one before the other, these are classical dynamical variables, it does not matter the order in which you write them, and this dependence on position and momentum gives the expression for the differential increment in the Hamilton's principal function as dH equal to the partial derivative of the Hamiltonian with respect to p times the increment in p, because where can this increment come from? It can come only from increments in p and from increments in q, because that is what the Hamiltonian depends on, and the corresponding coefficients will obviously be the partial derivatives of the Hamiltonian with respect to the corresponding parameters. So, del H by del P times dP plus del H by del Q times dQ, and I think it is always good to see this physics behind the partial derivative, so that you do not look at it as just mechanical algebraic mathematics or calculus. Through each term it is physics which is talking to us. The fact that there is an increment in Hamiltonian and this increment can come only from the increments in momenta and from the increments in the coordinates, because those are the quantities on which the Hamiltonian depends on, right. So, dH becomes this, and this must hold good for each degree of freedom independently. So, this is, now we have two expressions for the differential increment in the Hamiltonian. One is this and the other is this, right. Both involve arbitrary increments in the momenta and arbitrary increments in the coordinates, and they all add up to the same increment in the Hamilton's principal function. So, the corresponding coefficients must be equal, the better be, right, for each degree of freedom. So, the coefficient of dP in this, which is qk dot, must be equal to the coefficient of dP in this term, which is del h by del p. So, del h by del p becomes equal to q dot, and the coefficient of this dq, which is p dot, must be equal to this coefficient of dq over here, but mind you there is a minus sign over here. So, this is carried over here. Okay. So, these equations that you see at the bottom, del h by del p equal to q dot and del h by del q equal to minus p dot, are known as Hamilton's equations of motion. What do they tell us? They tell us how q and p evolve with time. That describes how a mechanical system will evolve with time. Now, that is the fundamental problem in mechanics. How do you describe, how do you characterize the state of a mechanical system, and how does this evolve with time? Its time dependence, its time derivative, what mathematical equation provides this time evolution? So, it is an equation of motion. It connects the position, velocities, accelerations. It provides an equation of motion, and these are known as Hamilton's equations of motion. I will take just a few more minutes and we will take a break. There are some issues which I have not gone into any further, any great depth. I mentioned them for those who are interested and intelligent and who would like to take proactive steps to read further, but I am not going to discuss them in this course. I have emphasized that this alternative formulation is based on the principle of variation, which requires the action integral to be an extremum, and I pointed out that this extremum could be a minimum, it could be a maximum, it could be a saddle point, and in more general terms it is what is called as a stationary point. There are complex questions that one can ask. Is the stationarity local, is it global? And these are fairly complex issues, fairly advanced concepts. They go well beyond the scope of this course. I will not get into those details. Usually one knows even from elementary calculus that we distinguish between a minimum and a maximum only by looking at the second derivatives, right. So, there are additional differentials which come into play, and I will not discuss that. And with this we are ready to conclude this particular class. I will mention a few references. There are some excellent papers in the American Journal of Physics which you will find very instructive. In particular, I like this title very much, Getting the Most Action Out of Least Action. This is really a very catchy title for a paper, okay, because the least action he is talking about is obviously the principle of least action and not the least action we always like to do, which is to do nothing, right. So, the least action is what Thomas Moore refers to, and he gets a lot out of it. So, the title is very nice, Getting the Most Action Out of Least Action, and there are other papers by Taylor and his collaborators Hanka and so on. you might find these papers quite instructive, and with that we will conclude this class.